Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 89. It's on mass energy equivalence. Remember, one of the greatest laws in physics is the law of conservation of energy, so the energy stays the same in a system or within an object. But remember, the matter, the mass inside that system, also has energy. Einstein showed us that using the equation E equals mc squared. So when we see certain interactions, let's look at the fission of uranium-235. We're releasing energy. And so uranium-235 is relatively unstable. If we hit it with a neutron, it becomes uranium-236, which is highly unstable. And it'll quickly break apart into krypton-92, barium-141, and then 3 other neutrons are given off. If another neutron hits another uranium-235, that happens again, and that could happen again and again. So we get this chain reaction. And so those neutrons flying around have a huge amount of energy. It came from the matter itself. And so we could tap that energy. So in a nuclear reactor, we could heat up the water surrounding the uranium. It then makes steam, which makes electricity in a generator. We cool down that water, and then we recycle it over and over again. And so the conservation of energy always occurs in an object or a system over time. The energy stays the same. But remember, any object or system is going to have matter, which has mass, and that can be converted into energy and back again using E equals mc squared. So in this video, I'm going to show you how to calculate the amount of energy that comes from mass in an interaction like that. And the example we'll give is fission. And so to talk about E equals mc squared, let me give you an example of that. This is carbon-12. Remember, carbon-12 is the standard. It's the standard upon which we figure out what an atomic mass unit is. It has exactly 12 atomic mass units inside it. 6 protons, 6 neutrons, 6 electrons. But if I were to take that and deconstruct that carbon-12 into its 6 electrons, protons, neutrons, we know what the atomic mass of each of those is. So it'd be 6 times the atomic mass unit of the electron, 6 times that of the proton, 6 times that of the neutron. If I add up all the individual masses of those subatomic particles, what I get is a larger number than the atom when it's all put together. And so what happens when we break it apart to that energy? It becomes mass. And as we build it back again, it becomes energy. So where did it go? The energy is in the binding energy. It's the energy that's holding that nucleus together with all those protons inside it. And so as we convert matter into energy and back again, energy is going to be conserved. And so let's go through that energy of fission again. We get the arrival of a neutron, and then it breaks it down into barium, krypton. And so what I'm going to do is show you how much energy is released in this one reaction. And so what you want to try to do is calculate it. You could pause the video right now and calculate it. Try it on your own. You'll have to know a few things. You have to know the atomic mass units of the uranium-235, atomic mass units of the neutrons, the barium, and the krypton. But all I'm going to do is figure out the mass change, and then I'm going to use E equals mc squared to figure out the amount of energy. If you're totally lost, let me show you how I would do that. So before the reaction, we had 2 things. We had the uranium-235 and the neutron. So I'm going to figure out the mass of each of those together. So I'm simply going to add those up, and this is going to be the mass before. I then figure out the mass after. So what do we get after? We get the barium, the krypton, and the 3 neutrons. And so I'm going to add those up, the mass of all of those. And you can see that we have a lower mass after. Now, where did that mass go? It became the energy. And so how much energy? It's going to be 0.189 units. So that's the mass change. And if we want to figure out the amount of energy, then we're going to have to use Einstein's equation, E equals mc squared. Remember, the units are going to be important. So energy is going to be measured in joules, mass in kilograms, and then the speed of light is going to be c. And so I set up my equation like this. You can see one problem right away, and that is that my units are in atomic mass units, but I have to use kilograms right here. And so we've got a conversion. 1 atomic mass unit equals 1.6605 times 10 to the negative 27th kilograms. And so I'm going to have to use that to figure out my mass. So I've converted it to kilograms right here. And then I just simply solve that. And this is going to be the amount of joules of energy that are produced when we lose the mass in that fission reaction. Now, it doesn't seem like much energy, but think how many atoms are going to be found in, for example, a kilogram of uranium. There's a huge amount of joules of energy that are being released when we have this fission reaction. And so did you learn to apply the conservation of mass and conservation of energy to solve a simple problem? I hope so, and I hope that was helpful.